This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
Every time an industrial factory line shuts down, you are witnessing the physical limit of a century-old technology. Modern machines depend on electromagnetic motors that generate force by pushing high currents through heavy copper windings. This process creates immense resistive loss, bleeding energy as heat directly into the motor core. Because these motors cannot efficiently produce high torque at low speeds, they require massive gearboxes to amplify force. This adds thousands of moving parts, each one a potential point of failure. The result is a cycle of friction, wear, and eventual collapse. In a legacy system, maintenance isn't a variable, it's an inevitable tax on production. Engineering has reached a ceiling. You cannot optimize your way out of the heat and friction inherent in electromagnetic induction. To break through that ceiling, we have to abandon Lorentz-force mechanics entirely and move toward controlled electric field geometry. This is Electrostatic Torque Fabric, or ETF. It replaces copper coils and magnets with multi-layered printed circuit boards that act as high-density electrode arrays. Instead of inducing current, ETF schedules voltage. By modulating electric fields within a specialized fluid, we shift the dominant loss behavior into a dielectric path, allowing the motor to generate force without the physical contact of gears. This architecture removes the physical mechanism of winding loss, providing a path to high torque motion without the thermal degradation that defines the induction motor. This technology is housed within the ETF node, a self-optimizing execution unit capable of autonomous field orchestration. This chart highlights efficiency at rest. A traditional motor draws continuous current to hold payloads, but an ETF node maintains its grip with near-zero steady-state loss. The AI kernel schedules these fields in time and space, maintaining optimal efficiency under changing industrial loads. Our immediate commercial wedge is the logistics sector. We are eliminating the gearbox in continuous-duty conveyor systems, replacing high-maintenance assemblies with a sealed direct drive unit. By focusing on high-maintenance conveyor belts, we are entering a $150 billion market where heat and downtime are chronic, unresolved pain points. Built for scale using PCBs and standardized electronics, a unit costs under 1,500 euros. Selling between 3,000 and 8,000 euros yields up to a 75% gross margin. For the customer, zero mechanical wear ensures a flat total cost of ownership. This supply chain is resilient. We are moving away from the geopolitical risks of magnet production and into the high-velocity world of precision electronics assembly. These margins provide the capital to aggressively displace incumbent magnetic architectures, which are structurally burdened by higher material costs and maintenance requirements. The strategy scales from a single conveyor motor to a distributed force network that can span an entire infrastructure. Over 20 years, we will evolve from discrete industrial motors to a connected fabric of force. This leads to the ultimate economic endgame, force as a service, where industrial capacity is a networked infrastructure of programmable nodes. ETF transforms force from an isolated mechanical output into a networked resource for industrial civilization. We are grounding this vision in an immediate 90-day sprint to validate our industrial pilots in real-world logistics hubs. We are seeking 2 to 5 million euros in seed capital for prototype validation, followed by 15 to 30 million for Series A manufacturing scale. This capital will convert validated field theory into the programmable infrastructure required for the next era of industrial motion.